were in the offline. But last class I was teaching light chapter, isn't it? I have taken 2 sessions on light chapter, completing the reflection part alone. Refraction was still remaining. But many students started messaging me to take magnetic effects of electric current. Maybe school exam, it may be there in the portion. So today I am going to stop light and start magnetic effects. In today you had exam. What topic you had? Magnetic effects of electricity. Oh, you already wrote the test. Okay. Anyhow, so today you are going to learn the chapter once again, and I hope it helps some people for the exam. So that is the reason for sudden switch from light to magnetic effects. Okay. So we'll complete this maybe today, if possible. Let us see, and then once again we'll move back to light chapter where we left. Fine. So 1 more minute is remaining to go live. We'll start once. Whenever you're coming for the live classes, carry your water bottles and everything, because you cannot go in the middle outside. So always have a practice of carrying the water bottles in the offline class. Online class they have liberty, they can off the camera, go and have water, eat something and come. Once you are here, you should be ready with you. Don't bring anything to eat here, not allowed to eat, but you can bring water bottle. Come soon, man. Raman sir, recording is on, no? Okay, we're going to go live. So good evening everybody. I hope you are able to hear me. And I want everybody to have their videos on. As I said, whenever there is an online class, you have to have your videos on. Please don't ask us to say you again and again to on your videos. Your videos must be on. So Shri Hari, last week you had a lot of off videos classes. So don't off your videos. When the class starts, video should be on. Okay. So I hope everybody is able to hear me and everybody is able to see me clearly. If there is any problem in connection in the viewing the board or viewing me or anything, you can ask me to stop and we can check is there any problem. Come fast, Charan. Put the red light on, Revan sir. So make sure that again I am repeating, videos should not be off. Nikhil Paul, Rishit, Javikshan, Satvika, Vijay, everybody, those who have joined in the online mode. You are in hometown. So hometown means what? When camera will not Okay, whatever. Mukesh, Rishit, Nikhil Paul, Ritika, Harish, make sure your camera is on and don't make me to say you again and again on your cameras. Okay, fine. So today as the plan, I have told already in the group also, based on the request of some children, today I am going to teach you magnetic effects of electric current. Don't worry why I left light in the middle, I will complete light, no problem in that. But many, not some, actually I got some 15-20 messages in WhatsApp that please take magnetic effects of electric current. So based upon that request only, today I am starting magnetic effects of electric current and I will be continuing the refraction part of light chapter in my upcoming classes. Okay. So without wasting much time, because we have only 1 hour in our hand, let us enter into the magnetic effects of electric current. I think some of you are learning it for the first time. So please take the notes properly. Earlier chapters you had notes. So now whatever notes are required, I will be keep on giving it to you. Keep on taking the notes properly, right? So first let us start this chapter, which is magnetic effect of electric current. And as the name says, the current which is passing through a conductor produces magnetic effect. And in this chapter, you are going to learn about that effect. Already in the previous chapter, You have learnt about heating effect of electric current. Am I right? Which was found by whom? Joule. Joule was a person who gave heating effect of electric current, where he told that heat energy produced whenever the current is passing through a conductor is H is equal to I square RT. Am I right? Here we are going to talk about the magnetic effect of electric current, which was found by whom? Hans Christian Ørsted. He was the person who first identified accidentally in the laboratory that electric current is also having some magnetic field around it. We will discuss in detail like how he found, what he found, and how to, what is required for you people. So I know, I hope you have that understanding that 10th standard and 12th standard are interrelated. Are you knowing this? Whatever chapters you are studying in 10th standard in physics, it is going to once again repeat in 12th standard also. You are studying light, light will come in 12th as ray optics. You are studying electricity, it will come as current electricity in the 12th standard. You are studying magnetic effect of electric current, it will come as moving charge and magnetism in 12th standard. So whatever you are studying now, that is the base for your 12th standard. If you are weak in 10th, these chapters, automatically you will struggle in 12th also. And if you are strong in these chapters now, automatically it helps you in understanding the context in 12th also. So be very clear. I will try to teach you in a way that you need not to mug up things. You can understand what is happening, and you should remember it, because it is not going to be useful only for 10th. It is also going to be useful for 12th. Fine. So this chapter, first let us see why, like where you see this magnets. So can you tell me where we see the magnets? I am talking about the magnets, any magnet. You can talk about permanent magnets or electromagnets. Where you are using magnets in real life? Motor, good. Electromagnets. School dress. Oh, belt. Okay, very good. Fridge. Junkyard, good. Or where else? Doorbell, isn't it? Doorbell we use. Yes. What? What one? This one. Oh, this stylus. Yes, very good. Magnet is there here also, where my stylus is touching the board. Yeah, very good. So these are some places where we are using magnet, isn't it? So magnet is not having only this much use. Magnet has tremendous use, and the more we get control over the magnets, the more we will be able to use it in the applications. Let me tell you one thing. Magnetic effect of electric current is there from last 100 years, 150 years only. Imagine before that. Found long before. Natural magnets. So already natural magnets were there. Then what was the need of finding this electromagnet? The problem with natural magnet is we cannot control the magnetic field of it. If you have a magnet, natural magnet, if it has a magnetic field of suppose 1 Tesla, then that is the magnetic field of that magnet. You cannot increase it, you cannot decrease it. You cannot make the magnetic field to be 0, neither you can make magnetic field to be high. What is the value? That is the value. Are you getting? The control is not there over the magnetic field. But once you are able to find, once the Christian Ørsted found that magnetic effect is there by current also, the biggest advantage was we were able to use it in a way that we can control it. Now you want magnetic field to be increase, you can increase. You want magnetic field to reduce, you can reduce. You want magnetic field to disappear, you can disappear. So magnetic field control came after magnetic effect of electric current was discovered by Christian Ørsted. Understand that. So it is the biggest discovery of that time, because now we can control the magnetic field. So wherever we were using magnets, now you can use electromagnets. In some places we still use permanent magnets only. That is because of its use. But understand that if you are having electromagnets, we have a stronger control over the magnetic field. That is the reason we are studying this chapter itself. So apart from whatever you have told about doorbells, about motors, generators, all these cases where we are having the magnets, we also have one thing. Have you heard about this maglev train? Maglev means what?
It's a type of magnet.
It is, no, it's not type of magnet. Maglev means magnetic levitation. The full form of maglev is magnetic levitation. So maglev trains are there. Where they are there? Which place? Spain. Mainly in Japan. Spain it is there. Later came. Where it was first used? Japan. Later it came in China. Now it is there in other European countries also. But what is this maglev train? And why maglev train is that much famous in those countries, developed countries? The trains, it goes at a speed 100 kilometer per hour, 120 kilometer per hour. Am I right? The best trains now in India, maybe you can say Vande. Tram is different here. Tram is very slow. I'm talking about trains now. I'm not talking about trams. I'm talking about trains. So in India, if you see, you are seeing trains around you, isn't it? The trains, what do you think will be the maximum speed? Generally, train runs at 70, 80, 90 kilometer. 100 kilometer per hour it's running. We are calling it as Vande Bharat Express, isn't it? Now Vande Bharat Express, the latest trains that we are using, it is having very good speed. 100, 120 kilometer per hour. 150 kilometer per hour is dream. India today, we cannot think about 200 plus kilometer per hour. But there are some countries who are running train at even 600 kilometer per hour. You know, it's almost like traveling in flight. There are places where people are able to use train, run train at how much kilometer per hour? Ajay, sit here. 600 kilometer per hour also. What is the meaning of it? Meaning is that trains can even go faster than planes. You know, in developed countries, people prefer train over the flights also. They will think in flight it will take more time than train. Formalities, going inside, boarding, checking inside, going, sitting, once again getting down, all the formalities, getting the luggage. They are preferring trains. Why? Because trains can run even at 600, 700 kilometer per hour. You know what is the problem in the normal trains? The friction between the tire, that is the rail is there, no? Rail and the wheels. Wheels are made up of steel, isn't it? That friction you cannot reduce it to the extent that it can go very fast. But in magnetic levitation, we completely by making the tracks like having magnets over it, and we will keep another set of magnets which will be lying in the base of the train. Can you feel what is going to happen? It's going to repel each other. North-north repelling, south-south repelling, north-north repelling, south-south repelling. Now this will make the train to literally be above the magnets, flying above the magnet. It won't even touch down, no friction. And then it runs the engine. I mean, I'm not going to the detail of that, but that's how the train runs. It is levitated. Levitation means to lift. You have seen Harry Potter movie? Anybody has seen Harry Potter movie? They will use a word, leviosa. Levitating means lifting something above, isn't it? So magnetic levitation means the train is lifted by the magnets and a train goes very fast. These kind of trains are called as maglev trains, magnetic levitation trains, which are there in the real world. Yes, please.
An example, bullet trains, sir.
Bullet trains. You are saying bullet trains, right?
Yes, sir.
Bullet trains are not maglev trains, man. Bullet trains are fast, but I am talking about maglev trains, magnetic levitation trains. They are faster than bullet trains. India now we are making bullet trains. By the first stretch going on between Bombay and Ahmedabad. Its work is going on. Another 2 years you will see bullet trains in India. But maglev trains are still not in the plans itself. Maybe after 5, 10 years, 10 years we may see. Okay, coming back to the topic now. This is just about how we are using the electromagnets. First, let us see, apart from that, MRI machines, speakers, there are many places where we are using the magnets in real life. Let us talk about the story how this magnetic field was found. As you told that magnetic, I am not talking about the magnets which are because of the current. I am talking about the naturally occurring magnets. You know where it was found? No, I am asking that. You have natural magnets, right? Natural magnets, where it was found first? Which place in the world? America, Europe. Anybody knows in online? Which place the magnet was found? Argentina. Say all the countries, something will hit. Africa, very good. India, Jerusalem.
Argentina, sir.
Say something, whatever countries you know, you are saying. You know how the name magnet has come? Are you aware about how the name magnet has come?
Magnet, sir.
No, magnet name has placed first in Asia. Magnesia is an island where in Greece. It's actually, I mean, Asia part, Asia Minor that time. So who found it? Chinese found it first. Near this place, Greece, the island name is Magnesia. Not island, it's a, I mean, kind of city, where the first time some stones were found, the stones were capable of attracting iron. The story is there. Shepherds were going, and shepherds were wearing shoes. Shoes had iron nail. Since shoes had iron nail, they, when they were going to that Magnesia island, no, their shoes were sticking on the stones. They felt something sticking. Till that time, there was no invention of magnet itself. When they dug out and took out a stone, they found something which is sticking on the iron. They are hanging that stone, it is orienting in north-south direction. That was the first time people found that there is something called as magnets, and the name was given as magnet because it was found in Magnesia island in Greece. Remember this very basic thing. It will not come in examination, but yes, it is true that it was found in Magnesia. And when this stone was held from the ceiling and left to move, it was waiting at north-south direction. That's why they were using it for navigation purpose. Suppose I want to navigate towards north, we will use that compass, magnetic compass. So they made magnetic compass by using this stones only. Earlier times, I am talking much long, when there was no magnetic effect of electric current. Until that time, magnets was only producing magnetic field. Nobody was having magnetic field by current that time. Okay. So the first person who talked about magnetic field. Okay, we will talk about that. First, let me ask you a question. You would have seen a bar magnet, right? So there is two poles in that, North Pole and South Pole. Can you tell me where exactly the North Pole is and where exactly the South Pole is? If I have a magnet, for example, if this is a magnet, it will have a North Pole and it will have a South Pole. Whether the entire half is called as north, like how I have drawn in the diagram, or whether the edge is called as north, edge, north, south. You think like that? Think like that, isn't it?
Yes, sir.
That is wrong thinking. Anybody knows? Entire. What Bharat? What do you say? That's what I'm saying. So you think that this end part is north, this end part is south. Am I right?
No, sir. Inside the lines are going straight.
Okay.
Magnetic field line.
Okay.
So
Which, from where to which point is north? Is north. Whether it is here.
Yes, south to north, sir.
Asking magnetic field lines how it is going. My question is, where is the North Pole? Whether I can say how I have drawn the diagram, half is north and half is south. Can I say like this? Or shall I say, oh, some are saying yes, okay, I will see. Or we can say this edge is north, this edge is south. Or we should say somewhere inside I have north, somewhere inside I have south. Somewhere inside north, somewhere
inside. Somewhere inside north, somewhere inside north. So
how much inside the edge? Can you tell me that also? Any idea? It is true actually, North pole and south pole of a magnet is not at the edge. It is always present a little distance inside the edge. And this length from north to south is called as magnetic length. And this is called as geometric length. These things you study in higher class only. For your information, I am telling you. If you have a magnet, its length will be its geometric length. But the distance between the north and the south will be the magnetic length. And magnetic length is always 0.87 times the geometric length. It means if you have 1 centimeter, 10 centimeter magnet, magnetic, it means approximately 0.6 and 0.6 would be the edges, inside edges we will have North Pole and South Pole. Are you getting now? So North Pole and South Pole are not at the edges, it is little inside the edge. So magnetic length is generally how much? 0.87 times the geometric length. Okay, now coming back. If I ask you, you have a magnet, this is the magnet. If I break this into two parts, will I get a North Pole and a South Pole? Two different magnets. Once again, if I break it, so can we have only North Pole and South Pole existing? No. even at atomic level. So I am breaking and to one of iron. Now also I will not have single pole. True, yes, correct. It can exist. Monopoles never exist. Magnets always exists like a dipole. Dipole means it will always have north south. If you break, you may think it is north and south, but no, it will be half north south. Once I break, you will think it is separate north south. So always magnets act like a dipole. Where you are writing in your brain, take out notebook and write. All of you, please start writing important things. Magnet is always a dipole. 0.87 I told. Magnetic length is 0.87 times the geometric length. I said that. One more thing I will tell you. Have you ever seen that if you ever buy a magnet, and if a magnet is dropped, its magnetic properties will go. Have you felt it? It will become a weak magnet. If you want, you can try it. You buy a magnet from the shop for playing and drop it many times. You will see after a few droppings, its magnetic effect, its magnetic power has come very down. You know why it is happening? Because the magnetic field inside the magnet is because of something called as domains, and these domains are oriented in the same direction. If the magnet is falling down many times, these domains will get disoriented, and so its magnetic properties will be lost. You will study all these things in higher classes. How magnet is formed, the magnet is in 10th scope. It is there in 12th scope only. But you should know that if a magnet is beaten with a hammer or it is dropped for a long number of times, its magnetic properties are lost. Remember this. Okay. So now coming to important topic of the chapter where you will have questions in examination: magnetic field lines or magnetic lines of forces and its properties. What are the properties of magnetic lines of force? Comes in the exam. You would have felt it. So about magnetic lines of forces. What is magnetic lines of forces? You can write. Those who are writing, please write. They are, please write, take the notes I am telling. They are imaginary lines. Around the magnet, which starts from north and terminates in south. Imaginary lines starts in north and ends in south externally, and moves from south to north internally, and moves from south to north internally, and moves from south to north internally. So they form closed continuous loop. This question has come 3 times in the board exam in last 6 years. So they form closed continuous loops. It will come in MCQ. This kind of question can come in MCQ. So magnetic field lines, what they form? They form closed continuous loops. It means it's not, as you see now, it is only visible externally, but internally also it runs from where to where? South to north. That is the property of what? Magnetic field lines. I will talk about this property in detail. So let us talk about the properties one by one, shall we? So first property you wrote already. Whatever you wrote now was the first property of magnetic field lines. So the first property is what you wrote now about magnetic field lines. What are these? So second point you can write: magnetic field is a quantity which has both magnitude and direction. It is a vector quantity. Magnetic field is a vector quantity. I hope you should know this. It is a quantity that has both magnitude and direction. And how do you find direction of magnetic field? Any idea? How do you find the direction of magnetic field? Anybody knows?
Compass, sir.
By compass you can find, or by drawing tangent you can find. Tangent to magnetic field lines. Suppose I have a magnetic field line like this. Please pay attention. And here if I am drawing a tangent, I will come to know what is the direction of magnetic field. If I'm drawing a tangent here, I'll come to know where is the direction of magnetic field. So magnetic field lines direction can be found by whom? By drawing tangent to the curve. Which curve? Magnetic field lines, right? So second point what you wrote was magnetic field is a quantity that has both direction and magnitude. Mention this also. Direction of magnetic field can be found. Write this point. Direction of magnetic field can be found. Direction of magnetic field can be found by drawing tangent. Direction of magnetic field can be found by drawing tangent on the magnetic field line. By drawing tangent on the magnetic field line. Right. Next property let us see. So, we have talked about the compass method. Yes, compass method also we can use, that you can keep the compass and you can see direction of magnetic field, isn't it? Are you able to see what they are doing? They are keeping a compass here, it points north south. Once again keeping compass, once again keeping compass, once again keeping compass. They are tracing the direction of magnetic field. So one way is by keeping compass, another way is by drawing tangent. Okay. So next property is that you already wrote. It starts from north pole and ends in south pole. And third property that also you wrote, inside the magnet its direction is from south pole to north pole and it is closed continuous curves, that you mentioned already, I think. Next, third point is very important. Third point is right, it is given there now. Relative strength of magnetic field is shown by degree of closeness of field lines. Important point. Relative strength of the magnetic field is shown by the degree of closeness of the field lines. It means if field lines are very close to each other, it is a strong magnetic field. If field lines are not close to each other, it is a point of weak magnetic field. Are you getting my point? First you write this, relative strength of the magnetic field is shown by the degree of closeness of the field lines. Degree of closeness of the field lines. Yes.
What is formula that 1 Tesla is equal to 10 to the power 4 Gauss?
That is the relationship between Gauss and Tesla. Why? We are learning that formula now. It's not required. Huh? Okay, good. That formula relates Tesla and Gauss. Both are units of magnetic field. Gauss also and Tesla also. So what you are saying is 1 Tesla is 10 power 4 Gauss is the relationship between Tesla and Gauss. You learn these things in the 12th standard. Okay. Anyhow, let me proceed further. I hope you have written. So now tell me, in this magnet, I have drawn a bar magnet here. If I take 2 points, one point here, point A, one point here, point B. Now this question is for point A or point B, which point will have more magnetic field, A or B?
Sir, the point B.
I have asked Charan actually. Okay, anyhow, you can try, but don't speak. You can put in the chat. Yes, Charan, please. Point B. Why? Reason. Reason only you learned now. See here, magnetic field lines are more close, isn't it? And see here, not that close. Here, if I draw a circle, I will be able to have 1, 2, 3, 4, 5, 6, 7 lines. Here, if I draw a circle, how many lines I am getting? 1, 2, 3, 4. So here it is more. So since the magnetic fields are more closer, they have a stronger magnetic field there. Are you getting? This kind of question also can come. They will draw the magnetic field lines and they will ask you which point has stronger magnetic field. What should be your answer? Where the magnetic field lines are more close to each other. I hope you are understanding this. Is it clear? Okay. Now, that's what it is represented. See how it looks like, the magnetic field lines. In laboratory, if you do experiment by keeping a magnet, you will sprinkle some iron filings. You know what is iron filings? When you, yeah, like from junk you get that iron scraps. And when you put all the iron filings, around and tap the board, then you see that all these iron filings are arranging itself in this continuous loop pattern. So you can see the magnetic field lines also from here, how it is there. Okay. So last point, but very important property of magnetic field lines is, write this, No two field lines can intersect each other. Why? Exactly.
Because two directions.
Yes, because just now we saw that tangent drawn to magnetic field line will give direction. If you have two lines intersecting, what is the problem? You know, I'll draw and show you what is the problem. See here, one line, another line. If they are intersecting at this point, one person can draw tangent like this also, another person can draw tangent like this also, isn't it?
Yes, sir.
So that is not possible. Two directions of magnetic field, so magnetic field lines will not intersect each other. This question also comes in the board examination. First, will they ask whether magnetic field lines can intersect? No. Why not? Because if they intersect, at that point we will have two directions of magnetic field, which is not possible. Is it clear? What? Then also they will not intersect each other. They will repel or they will attract. They will attract means they will form some very close loops. They will not intersect each other. Okay?
Sir, can you tell the reason again?
I said that, write if you are writing. Magnetic field lines cannot intersect each other because if they intersect, there would be two directions at the same point. Because if they intersect, there would be two directions at one point, which is not possible. Which is not possible. Can I proceed further? If you permit me. Shall I? Yeah. So, next we will talk about the magnetic effects of electric current. I said you, who was the person who found this is Mr. Hans Christian Ørsted. He was the person. In 1820 only we came to know that electric current can have a magnetic effect. Before that, we had that only magnets can produce magnetic field. Only in 1820, we really discovered that yes, magnetic field can be produced by electric current also. And how he found, you know, in laboratory he was doing some experiment. Yes, and suddenly he saw there is some deflection happening in the needle. In the laboratory, he was doing some circuit experiment, and there was some magnetic needle kept, magnetic compass kept, and his magnetic compass was deflecting when he was doing some experiment. He thought initially, okay, something is by mistake. Then once again he did, it was once again deflecting. Then he brought the magnetic compass nearby, tested various places, it showed different waves of deflection. So he understood, okay, magnetic field is produced by current also. So he also discovered radio, TV and fiber optics, not required for you. Okay. So first we will talk about the magnetic field for a straight conductor. Give the heading as, all of you please who are writing for the first time, if you are writing, give the heading as magnetic field for a straight conductor. Magnetic field for a straight conductor. Those who are writing for the first time, please take the notes properly. Magnetic field for a straight conductor. So see, before I start talking about this, I'll tell you the intention of Christian Ørsted. Please pay attention. So Christian Ørsted, when he found that there is magnetic field by electric current, what he thought the first thing was, he wants to replace the bar magnet. Wherever the bar magnet is used, he wanted to replace the bar magnet with something like a current carrying conductor. Okay. So for that, what was the magnetic field of a bar magnet? I hope you know, remember, magnetic field of a bar magnet is something like this, isn't it? Just now we saw no diagram. Am I right? This is the magnetic field of a bar magnet, and he wanted to have a magnetic field similar to this. That was his intention. So to find a magnetic field similar to this, what he started doing, he took wire. First he made straight rod and found its magnetic field. He made it as a closed circle, he found its magnetic field. He made many loops, he found magnetic field, and then only he discovered something which can have exactly replica of bar magnet's magnetic field, which is called a solenoid. We'll come to that. But before that, let us see the experiment that he conducted. So he took a cardboard, and on the cardboard he made a hole. So he took a cardboard like this, he made a hole in the middle, and he passed a wire through this cardboard. He connected the wire with some battery cell, some source of EMF, and then he on it. When he on it, current flown through this. On this board, he spread some iron filings. Okay, and once he started the current, he tapped the board like this. He saw that all the iron filings are aligning themselves, are arranging themselves in closed concentric circles. So he found, okay, if we get current carrying conductor, the magnetic field will be concentric circles. So if I show you the experiment, he took the cardboard, passed the wire through it, connected the wire with a circuit where he can give current inside. When the key was switched on, since the battery positive is here, negative is here, how will the current flow? From positive to negative. So when the current started moving from positive to negative, then he observed that these iron filings which were kept on the board randomly started orienting themselves in this form. Which form? Concentric circle. So what we came to know? We came to know that magnetic field due to a straight current carrying conductor is having what shape? Concentric circle. First thing we found, shape we found. Next was, he changed direction. Now what he did? He made plus to go above, minus to come down. Polarity changed. Then he tried to find the magnetic field. Then also he got same concentric circles. Whether the current is going from down to up or up to down, the loops are only concentric circle, but difference was there. Difference was direction of these loops. Now the problem was how to find direction. So to find direction, he used compass. He kept compass and tried to find how. And when he kept the compass, he found direction is in such a way that it obeys right hand thumb rule. And what is the meaning of right hand thumb rule? Right hand thumb rule says that, please pay attention guys, important. It says that when you hold a current carrying conductor in your right hand, not literally, imagining, current carrying conductor in right hand in such a way that thumb is pointing towards the direction of current. That time the four fingers will give the direction of magnetic field. I will repeat this. If thumb is pointing towards the direction of current, then the four fingers will give direction of magnetic field. See, don't think what you studied is enough. I am going to do some extra things today and that will be very useful in 12th standard. Understand this concept very well. So how you should find? If you have the straight current carrying conductor, your four fingers, they will give direction of what? Magnetic field, isn't it? So if the current is in the upward direction, you can see it will be like this. What is this? Anti-clockwise. If the current is downward direction, how it will be? Clockwise, isn't it? But the limitation is not only up and down, right? You may have wire like this also. If I draw here, if I draw like this, please pay attention. If I draw a wire like this, and if I ask you, what is the direction of magnetic field at point A and point B? Can you tell me? Sai Prasad, right? You are Sai Prasad only, you know? Yes, I'll give chance. Sai Prasad, can you please tell me direction of magnetic field at A and B? Towards whom? Me, you. I'll come to you. Yes, Mr. Mukesh. Sukesh, yes, Sukesh. Tell me, Sukesh. Point A and point B, direction of magnetic field. I am asking, what is the direction of magnetic field at A and what is the direction of magnetic field at B? Any idea? Bhupesh? Oh, A clockwise, B anti-clockwise. Okay. Sanchita, what is your thing?
A anti-clockwise.
And B?
B as
Clockwise. Great. All are saying wrong. A to B. Srinidhi is saying from A to B. No. Anybody who wants to say the answer from the online people? Nikhila, any answer? Direction of magnetic field at A or B? Yeah, please.
Sir, A north and B south.
No, wrong. Anybody else?
Anti-clock.
Sir, both A and B anti-clockwise.
Both A and B anti-clockwise. No, definitely not correct.
A is clockwise. A is clockwise, B is anti.
That's what I was trying to say you. You don't try to always think the answer should be clockwise or anti-clockwise. That is the first mistake you are doing. Use right hand thumb rule only. But see what you should do. Yes, tell me, man.
Sir, when viewed from the right, it will be anti-clockwise,
Hmm.
and from the left, it will be clockwise.
First of all, I said now, just now I said, don't limit your thinking to clockwise, anti-clockwise, because the answer is not that. Okay. Generally, what we think, straight current carrying conductor, answer will be either clockwise or anti-clockwise. No. Why it should be? Let me tell you. See. Since the current is going towards right, what you will do? You will place your thumb in that direction. All of you who are writing in the home, draw the wire in your notebook and check, put your hand and check, then only you will get the feeling. So when you keep your hand in the towards the right hand side, at point B, your fingers will try to go inside. Am I right? Is it right to go inside? So at B, the direction of magnetic field will be into the plane. It is called as into the plane. Into the plane. Into means inside the plane. And if you see the point A, my fingers are trying to come outwards. Can you feel it? My thumb towards right, my fingers are trying to come outside the plane. Out of the plane. Like this, we represent by a dot and a circle. So what is this? Out of the plane. I hope you have understood, those who have joined online. Are you getting? Don't limit your thinking to clockwise, anti-clockwise. If I ask generally wire taking current upwards, yes, anti-clockwise. Downward, clockwise. Correct, no problem. But now I am asking you, wire this plane, down, what is the nature of magnetic field? It will be into the plane. Upward, out of the plane. I hope you have understood this. Is it clear to you? I'll give another example to you. This question is for Sivesh, who has joined online. Please, Sivesh, turn on your mic and say me. I have drawn a wire and current is going in the upward direction. Point A, tell me direction of magnetic field. Very good, into the plane. Correct. Spontaneous answer. Very good, Sivesh. You can rule. Your fingers are trying to go inside, isn't it? So obviously, what will be direction at B? Out of the plane. Why? Because if you put your right thumb here, then your fingers will try to come out in this B point, isn't it? This kind of questions are coming in the board exam also. Into the plane, out of the plane. And how we represent it? If I put a cross sign, it is into the plane. Dot sign, out of the plane. Understood? This is called as into the plane, this is called as out of the plane. So you should know how to use the right hand thumb rule wisely. Don't think that answer will always be clockwise or anti-clockwise. I hope you are clear in this. Is it clear to you? If yes, shall I proceed further?
Yes, sir.
Yes. So,
Yeah, sir.
yes. So right hand thumb rule I have explained to you, and this is what it says. Yes. Why we are using? To control the amount of current. Whenever you see a rheostat, understand that it is going to control the current. What they will do, they will increase the current, they will decrease the current, and they will check whether the magnetic field is increasing or decreasing. We not only want to find the shape of the magnetic field, we also want to find how it affects the magnetic field. Are you getting? So straight current carrying conductor, when we increase the current, we saw that magnetic field is increasing. Decrease the current, we saw magnetic field is decreasing. So we came to know that magnetic field is directly proportional to current. Second thing we saw, the magnetic field at this point, near point, and the magnetic field at the second point, the far point, are not same. Inversely proportional. It means as you go far, magnetic field will reduce. If you are near to the wire, magnetic field will be more. We will write both the points now. So if you see what we come to know that these things I have told already to you. Yes. So we found that when the current is increasing, magnetic field, see, more magnetic field came. And when the current was decreased, magnetic field also decreased. See here, magnetic field lines became very, are you getting? So this gives us an idea that this straight current carrying conductor, if the current is flowing through it, how it affects the magnetic field lines, right? So I have noted that, also I have written here. You can note it down. It's an important thing. Please note it down. Magnetic field.
Can you show the right hand thumb rule once again?
You want to write it?
Yes, sir.
Okay, write it. I am showing once again right hand thumb rule. Those who want to write can write it. Yes, please. If you want to write, you can make a note of it, those who want to, not a compulsion. Yes.
Can you explain that corkscrew?
Same thing, right hand thumb rule is only called as corkscrew rule also. Corkscrew why we are saying, because if you are trying to open the screw also, see, when you suppose you are having a screw and you are tightening it by a screwdriver, imagine like that. So when you want to make it go inside, what you will do? You will rotate clockwise, and you want to make it come outside, anti-clockwise. So the same thing, if the current is going like this direction, it will be clockwise. Current is going outward, it will be anti-clockwise. That is only called a right hand screw rule also, corkscrew rule. Both are similar. Those who are writing the right hand thumb rule, please let me know when you are done writing. If you are writing right hand thumb rule, let me know when you are done writing. Can I go to the next slide? Somebody asked me to show this slide, whether the girl wrote this.
Yes, sir.
So I am proceeding further. Shall I? I hope I can. So this is the point which I want to say. Yes. This is the point I want to say stressfully, that magnetic field is proportional to current and magnetic field is inversely proportional to distance. So if they ask you, there is a straight current carrying conductor, one point is 2 meter away, another point is 3 meter away, which will have more magnetic field? 2 meter away point, isn't it? They may say the current in the wire is increasing, how it affects the magnetic field? Magnetic field becomes more stronger, right? These kind of questions can come in the examination. Is it clear to you? Is it clear to you guys? I hope it is.
Yes, sir.
Yes. So now I have a small question for you, and a very basic question, which who will answer is from online. I will take Sudarshan. He will answer. Sudarshan, unmute yourself.
Sir,
Yes, give a try. So AB is a wire. I have drawn on the board. You can see the wire, and there is 2 points. One point is P, distance of R1. One point is Q, at distance of R2. First of all, tell me the direction of magnetic field at P and Q. Second part I will give to somebody else. You just answer the first part. Yes.
in P in the plane,
Very good.
in Q out of the plane.
Very good. Very good. In P into the plane, at Q out of the plane. Next question is for Satvika. Satvika, you have to answer the second part. Second part is, given R1 is more than R2, where will the strength of magnetic field be larger? At P or at Q?
Yes, sir.
At P. Why? They are saying R1 is more than R2. Satvika, please understand that. R1 is more than R2, distance becomes more, magnetic field is reducing, no? Magnetic field is inversely proportional to distance, right Satvika?
Yes.
So what will happen? At Q it will have a higher magnetic field compared to P. Do you understand this?
Yes, sir.
Yeah. So that's what is the answer, and it is given here also. The first thing is into the plane, and second thing is magnetic field is stronger at Q compared to P. Simple question, isn't it? Fine. Then what? As I said, you Oersted continued his experiment. After doing the straight current carrying conductor, next he took a circular current carrying loop. So the next heading is magnetic field produced by current through a circular loop of conducting wire. Please make a note. The second is magnetic field produced by current through a circular loop of conducting wire. I see some students in online are giving request for recording. Don't worry, we are recording all the classes. You can share in the group if you want. So don't worry about recording. All the classes are getting recorded by us itself, and we will share the link with you if you want to see the video once again. Somebody was asking to record. Okay. So shall we start the next topic? Okay. So next is what? We took a wire and we took a wire in circular shape. Now we bend in the circular shape, and we wanted to study how the magnetic field lines will be around this. So same way, we took a board. In the board we made now 2 holes, one hole here, another hole here. We passed the wire through this hole, 2 holes, and down we put a circuit and we made the current to pass through it. And we spread some iron filings on the board, tapped the board and see how the iron filings are arranging themselves to know the direction of magnetic field. So when we did that, that is taking a circular loop, taking a board, making two holes, passing the circular loops through the hole and then connecting the bottom of the circular loop with the connection where we have the again rheostat and we have the battery. Rheostat is to control the amount of current and battery is to provide the electromagnetic, that is EMF, electromotive force. And we saw that the plus to minus means current will move in this direction. When we spread the iron filings and we tapped the board, we observed that the magnetic field lines, they are aligning. You see how they are aligning like this. Once again like concentric circles. But here it is going upward, so it will be in which direction? Anti-clockwise direction. At Q it is going downward, direction will be clockwise. Are you getting my point? At P I am getting a anti-clockwise direction magnetic field. At Q I am getting a clockwise direction magnetic field. In center I am getting a nearly plane magnetic field, that is straight line magnetic field. You see I have drawn here. So at P by using right hand thumb rule we found direction of magnetic field, at Q also we found direction of magnetic field and between it was like this straight. See, this is the point where Oersted was very happy because now he was able to feel something like I am getting similar magnetic field as the bar magnet, because when he saw this he got some excitement. I'll show you why I am saying this. So see here, these 2 points is having and in center we have the straight lines. So one more thing I'll say you before I talk about that, that in this case please make a note of this, the magnetic field is proportional to current and magnetic field is inversely proportional to radius. In that case, in the previous case I said magnetic field is proportional to current and magnetic field is inversely proportional to distance. Here I am saying magnetic field is proportional to current and magnetic field is inversely proportional to radius. It means you know what, if a question comes in the exam like there are two circles, one circle having a small radius, another circle having a big radius, then if they are having same current, suppose 2 ampere and 2 ampere, if I take the point here point X and one point here point Y, which point will have more magnetic field, X or Y? Yx. Shorter radius will have more magnetic field, that is what the point is. Lesser radius will have more magnetic field.
Are you having a chemistry class today?
Yes, it will be there, man.
Yeah, no.
Yeah,
Fine,
yeah.
fine.
Wait there. 7:15 you come.
Okay, thank you.
Yeah. Sorry. So I hope you are getting the point. A bigger circle has a bigger radius. If it has a bigger radius, it will have a lesser magnetic field. That's what this point says. It says that magnetic field is inversely proportional to radius. This kind of questions are coming. Two loops, 2 centimeter, 3 centimeter, carrying current of 5 ampere. Which loop will have more magnetic field in the center? A smaller loop will have more magnetic field. A bigger loop will have less magnetic field. These things we found experimentally, and in 12th all these things will become formula. Magnetic field due to a straight current carrying conductor will become equal to mu naught I by 2 pi r. Mu naught is a constant, I is the current, divided by 2 pi r, with r is the distance. Magnetic field due to a circular current carrying conductor at the center will become equal to mu naught I by 2 r. Magnetic field due to a circular current carrying conductor at an axial point will become equal to mu naught I a square by 2 into r square plus x square power 3 by 2. So these things will come in the higher class, and these things you can understand only if you are good in this. There nobody will teach you all this. Don't expect once again they will teach you. There they will say as we learned in 10th standard, and they will start directly from B is inversely proportional to radius, directly proportional to current. So B is equal to mu naught I by 2r. Okay, coming back. B is
Directly proportional to turns.
third.
Turns.
Yes, number of turns also correct. If you have more, but we, see now we are talking about a single loop and a single wire, straight wire, right? In case I am taking only one turn. If you increase number of turns, it becomes solenoid, isn't it? Same thing is going to happen now. Next, what I am going to do, I am going to take this magnetic field. Now, see, I said you the main intention was to find the magnetic field similar to whom? bar magnet. And he saw that this magnetic field by the circular current carrying loop is showing some similarity with this magnetic field. What he did, he kept many circular turns and he combined everything, and then he felt like when I do it, I will be able to get a magnetic field similar to the bar magnet. And the same thing happened, you see. Next, if I am going to draw a solenoid where I am going to have, see, wires wound like this, they are going to combine and then produce a magnetic field which is very similar to what? The bar magnet's magnetic field. See here, can you feel that? Now it behaves like a south pole, it behaves like a north pole. So first you should write what is solenoid. Give the heading as solenoid. Give the heading as solenoid, and definition is mentioned there above itself. Definition is coil of many circular turns of insulated copper wire wrapped in the shape of cylinder. Please note it down. Coil of many circular turns. This question came in the last year board exam paper also. Define solenoid. A coil of many circular turns of insulated copper wire wrapped in the shape of a cylinder. Wrapped in the shape of a cylinder. This is known as solenoid. What is solenoid? Take a wire and turn it like what? Like a cylindrical form, and pass current through it, it becomes solenoid. And since it becomes solenoid, it will have a magnetic field very similar to bar magnet. One more important thing is there, I'll talk about that also. Yeah. Inversely proportional to? Resistivity or resistance plays no role in the magnetic field. Remember that. But yes, because of resistivity and resistance, current may change, and that may change magnetic field, but not directly. No formula of magnetic field has resistance involved in this. Whatever magnetic field formula we know, in no formula of magnetic field we will have resistance involved in that. Okay. Shall I proceed further? Shall I? Okay. So now, in exam if they come, draw the magnetic field pattern of solenoid, you will draw something very rubbish. Most children have seen how they draw. They draw like this, and then they draw this, and when they draw, they intersect these lines. That's where you lose marks. In board examination, if you intersect these lines, no, they'll cut marks for this. When you are drawing a solenoid, see how beautifully I have drawn. I have not drawn, the computer has drawn. Nothing is touching each other, right? The same way you should draw in the board examination. If the question is coming, that's why now I'll teach you that also to you. So one thing you should write before I tell about how to draw the magnetic field. Write this: magnetic field is proportional to current. Magnetic field is proportional to number of turns, and magnetic field obviously we know is inversely proportional to radius of the coil. One second question can come from here. I should write one thing: magnetic field is proportional to number of turns per unit length. You add here number of turns per unit length, not just number of turns. Number of turns per unit length. Positive cause south and negative cause, yes, always. Always remember, positive terminal will make a south pole and negative terminal will make the north pole. Remember this diagram. These things are important for the school examination. In solenoid, wherever you have the positive terminal, that side will become a south pole. Wherever you have a negative terminal, that side will become a north pole. Okay. So I have a question for everybody, online, offline, everybody. There are two solenoids. One solenoid has 100 turns. Another solenoid has 200 turns. Which solenoid will have more magnetic field? 200, right?
200 turns.
Yes? Yes? No. You should ask me, sir, what is the length of both? Until I say they have same length, you should not say the answer. Okay. If one is having 1 meter, another is having 2 meter, which will have more magnetic field? 200. No, both will have same magnetic field. You know why? Number of turns per unit length is same, no. 100 turn by length is 1. 200 by 2, what is that? 100 only, no? So there are two solenoids, one is having 100 turns 1 meter, second is 200 turns 2 meter. They both will have same magnetic field. Are you getting my point? That's why I added here per length. It is not depending upon number of turns, it is depending on number of turns per unit length. If number of turns per unit length is like, if you have 100 turns in 1 meter, it will be 100. If you have 500 turns in 5 meter, it will be still 100 only. Are you getting my point? So number of turns is not directly linked with the magnetic field, it is linked with number of turns per unit length. I hope you have understood this. And as I said, if the question comes in the school examination to draw the magnetic field lines for a solenoid, then what you should draw a solenoid, how you should draw. See, first you just draw, they have to 11 lines, but you can draw how many lines you want, 10 lines you can draw. And when you draw the lines, after that you erase the extra, that's much deeply they are telling. See, like small children they are teaching you. Huh? What? Okay. So then you have to draw a solenoid around it. By freehand you can just draw a coil, and then you can draw the lines of forces. How you will draw? By combining them. See how I am combining? See, if you do like this, you will avoid intersecting the lines. Are you seeing how they are drawn? If you draw like this, you will get full marks in the board examination. If you by mistakenly intersect two lines, they will cut marks for this. Remember that, because magnetic field lines can never intersect each other. One more thing I will tell you. The solenoid's magnetic field inside are uniform. So magnetic field at every point inside solenoid is always same. Are you getting my point? If you have if you have solenoid, inside the solenoid there will be what? Uniform magnetic field. It means that any point you take, suppose one question has come like this also. See how the question has come. Like this. Solenoid is there. Taken point A, taken point B, taken point C. Which point has maximum magnetic field? A, B or C? A, C. Huh? None. Obviously none. All are having same magnetic. Just now I told no. What I said, magnetic field inside solenoid is uniform. Why? What is the meaning of that? Uniform magnetic field means all the points inside solenoid will have same magnetic field. And you know one thing, outside the solenoid, the magnetic field will be less. It will not be zero, it will be small. If I take a point outside, magnetic field will be very, very less. So always remember, magnetic field inside the solenoid is uniform. Magnetic field outside the solenoid is almost negligible, it is zero. Is it clear? And for what we use solenoids? Soft iron. We are using for 2-3 things. First thing is, if you want to magnetize some material. If you have soft iron, it will become temporary magnet. If you have hard iron, it will become permanent magnet. If you keep that iron inside the solenoid and pass current, magnetic field will magnetize. So first application of solenoid is to magnetize the magnetic materials. Second application, it is used as electromagnets in many applications, like for example, junkyard. Electric motors, they are using solenoid? Nowhere, no. They are using in MCBs. MCB is miniature circuit breaker. Have you heard about that MCB? In home also it will be there, right? If there is some problem in the current, it falls down. Why it falls down? It is acting like a fuse there. I will talk about that in the next class in detail about MCB. Remember that solenoids are used in what places? They are used in magnetizing the magnetic materials in junkyards, electromagnets, MCBs. Question has come like this. What are the applications of magnetic solenoid? Okay, so as I said, iron scraps. You see here, inside solenoid will be there. They are attracting all the junk from the iron, from the junk, and they will go and they will drop it whenever they want to drop it. See, if you have seen these kind of things on the road, right? Big iron things are going. Do you think they will use labors for lifting and dropping it? Never. They will have cranes which will have electromagnets. Then on the electromagnet, it will attract it. They will take it to some place. They will drop it. When they off the current, magnetic field goes. On the current, magnetic field becomes very high. Are you getting? One more question comes in the board examination. How do you increase the magnetic field of a solenoid? By increasing number of turns per unit length, you should write. By increasing current, and third thing is by introducing a magnetic material inside the core, in the core of the solenoid. Once you introduce a magnetic material, it will increase the magnetic field more. Okay, these questions are coming in the examination. I will take stop here because next class has to start, and I will continue in the next class, and I will complete this chapter. Only small topics are left. I will be taking those topics in the next class. Okay, so I hope whatever I try to teach you understood. I will continue in the next class, maybe, and we will complete this chapter at that time. Okay, take care. Bye bye. I am dropping off. You can also drop off. Bye bye, guys. Take care. Good night.
Thank you, sir.
Yes.
Thank you, sir.
Bye bye.
Thank you, sir.
Thank you, sir.
You can end the meeting, Revan sir. End the meeting.